Welcome to Module 5 on genomic selection, where we're going to continue to look at whether genomic selection works or not based on information in the literature. And in Module 5, we're going to talk about how Scheme 3 has been used to assess the effectiveness of genomic selection. And just to refresh your memory, in Scheme 3, shown down here at the bottom, you take individuals selected from the training population, make crosses between them, and develop prediction populations. So in this scheme, you're actually doing selection and breeding, crossing, recombination. And so this is really the most realistic way to assess genomic selection because you're actually using it. And then you can phenotype progeny from these prediction populations to see how good genomic selection is working. And here's the first paper. It's going to look at resistance to stem rust in spring wheat. Here's the training population, the 374 lines out of the Simmons International Stem Rust Nursery. I'm referring to this as training population 1 because there is a second one that we'll talk about later. They use historical data from stem rust collected on these 374 lines from Ethiopia and Kenya over about a 6-year period. And each of these 374 lines was tested in at least 4 environments. So this is basically an unbalanced historical data set being used to build the prediction model. These are genotype with almost up to 21,000 markers using genotyping by sequencing. There is a second training population, consists of the same lines and same data as in training population 1, but now it's been supplemented with 84 lines out of cycle 0, as they refer to it. These 84 lines are quite important because they are the parents used to generate cycle 1 and cycle 2 lines coming out of genomic selection. And here's the phenotyping information on that second training population. Here is the schematic of how they did this study, and these schematics are going to get a little more complicated than what we saw for cycle 2 because now you're doing more crossing to go through cycles of selection, genomic selection, in some cases phenotypic selection. So here's our training population 1 shown up here at the top, and that data is used to build a GS model that can be used in predicting the value of the individuals in the genomic selection scheme. They also selected 14 lines from that training population and made crosses, 84 four-way crosses amongst them. That's only 4% of the training population being sampled to generate the rest of the germplasm in this study. The hybrids were selfed. They got F2s. Now they're going to do a little bit of phenotypic selection. So those F2s are also selfed. They get families. Those families are phenotyped. And now that phenotypic data and the genotypic data on those families and now can be added to training population 1 to create training population 2 and create a new model that can then be used in genomic selection using data from both of those sets of lines. From those lines, they also selected the 5 best based solely on phenotypes, and those are your phenotypic selections that will go into the field studies. Now, those F2s, they also selected those using data from training population 1 and genomic selection, selected the 5 best of those F2s, intermated them, self the hybrids, and got cycle 1 F2s generated from 1 cycle of genomic selection. Those F2s were also genotyped, and now they use the second training population model that contains the parents of these cycle 1 and cycle 2 F2s. To do genomic selection, select the 5 best, intermate them, and get the hybrids. These hybrids are selfed to get F2s from a second cycle of genomic selection. All these selections from these different populations are all selfed, and then all those selfed progeny can be put in the field test as described there. So let's look at the results here. Oh, I should explain that in the study from each of those populations, they take the progeny and split them in half. So they have basically a replication of whether that scheme has, of the effect of using that scheme. So they call that split 1 and split 2, but let's just focus on the mean of those two splits. Okay, the mean of how well this is working. So cycle 0, shown in the blue bar, is no selection, and you can see there that it's fairly susceptible to stem rust, as you might suspect with unselected lines. Let's look at how the phenotypic selection did. It worked pretty well. Okay, disease severity has certainly gone down, as you expect, with effective selection. Now, lines come out of the first cycle genomic selection was based on the first training population using only the 374 lines. It was also somewhat effective. They are more resistant than the unselected lines in cycle 0, but certainly they're not as resistant as the progeny that are coming out of the phenotypic selection. And then the second cycle of genomic selection, the C2 lines, they use the second training population, and they certainly are more resistant than what the GS lines coming out of cycle 1, but they're still not quite as good as those phenotypic selections. One thing to note here is that the GS, the ones coming out of cycle 2 of genomic selection, are better than this first cycle, and the accuracy of the model used in that stage of selection, was actually quite a bit more accurate than the model that was used in generating the cycle 1 lines. And as we know from some of our previous discussions, with a more accurate model, you should get a better gain from selection, and that certainly seems to work here. 2 cycles of genomic selection decreased disease by 31%, and the 1 cycle of phenotypic selection decreased disease by 42%. Our gain per cycle was actually pretty high for phenotypic selection and genomic selection. The 2 cycles of genomic selection takes about as long as 1 cycle of phenotypic selection. And it should be noted here that phenotypic selection for stem rust really doesn't take a whole lot of time and not many seasons, because you don't need a lot of seed or not a lot of seasons to get pretty accurate phenotypes to do your selection with. So gain per unit of time is really not significantly different between these phenotypic selection and genomic selection. So I think you would conclude here that genomic selection was worked and was effective at decreasing stem rust, as was phenotypic selection. Now look at another example of using scheme 3 to assess genomic selection, and this is looking at grain yield under drought in African maize. And here are our training populations, 8 maize biperennial populations from each of the drought-tolerant maize in Africa program, and 8 more from the water-efficient maize in Africa program. And each of these biperennial crosses, they generated anywhere from about 150 to 300 F2-derived families per cross, and each of those F2-3 families was test-crossed to a common tester. They were phenotyped. I'll skip over the details, but there was genotype for yield under drought environments and under well-watered environments. The parents and high yield checks were also included in this phenotyping. And here's some information on the genotyping, and you really don't need a whole lot of SNPs to get some pretty accurate predictions in maize. And here is a schematic of the process they use to generate the populations to evaluate the phenotypic selection and genomic selection. So here is your cycle 0, which becomes the lines that are going to be used as your training population, and they're all genotyped and phenotyped as test crosses. And here they pretty much did 1 training population from each of the 8 crosses for each of those 2 projects. Each biperennial cross by itself was quite large, and they could build a training model within each of them to do the selection with. They also did phenotypic selection. So from the cycle 0 F2-3s, they started going through pedigree selection, visually picking the best ones up to the F5 generation, and those are what they call the pedigree selection. The genomic selection part is here. From these, based on phenotypes only, they go through the first cycle of selection, selecting the top 10%. Those are animated, and they get a progeny from those. Now use data from the training populations, and build a GS model and select the top 10% of the individuals based solely on their genetic values based on genomic selection. They intermate those, and that's completed 1 cycle of genomic selection, and here they refer to that as cycle 2. Cycle 1 is phenotypic selection. Cycle 2 is genomic selection. Based on the F2s there, they get genomic selection and select the top 10% of those from each cross, intermate them, and come up with cycle 3, which also is resulted from genomic selection. To assess this, they take those selected individuals, they do the test cross with each of those, and those test crosses are then phenotyped as described here in this box. And let's see what the results were. Over 3 cycles of selection, which includes 1 cycle of phenotypic selection followed by 2 cycles of genomic selection, yield under drought was increased by 13.4%. Of that 13.4%, 7.5% was due to genomic selection, which was done in cycle 2s and cycle 3s, and 5.9% was due to cycle 1 of phenotypic selection. So here's your unselected population. Let's just look at water efficient maize. And the yields were not that great. They're a little bit better though than your high yielding check varieties. You go through 1 cycle of phenotypic selection and yields increased quite dramatically. 1 cycle of genomic selection didn't change much from phenotypic selection in this set of lines, populations. And you go to the cycle 3, which is genomic selection, and yield is increased. Same general trend in drought tolerant maize, and looking over all the populations, again, we see that the 3rd cycle, which results from 2 cycles of genomic selection, is the highest yielding one. So certainly here you conclude that genomic selection is working. Phenotypic selection worked in that 1st cycle, and then 2 cycles of genomic selection increased yield even further yet. And really from all of these, the yields are significantly greater than what we see from the high yield checks. They also calculate out what was the gain per year, as shown down here, going through their 3 cycles of selection, 1 of phenotypic selection, 2 of genomic selection. The gain was 0.07, and they compared that to what has been reported in the literature, gains per year. And you can see that their gains per year for yield under drought was quite comparable to what other people are finding, actually much better than what people are finding under drought in most conditions, and actually quite comparable to what people are seeing under well-watered and highly productive environments. So certainly here you conclude that genomic selection for yield and for drought tolerance in maize has been working. With that, we'll continue on to the second part of Module 5.